Welcome back, everyone, to today's Explainer. Today we're going to dive into what is easily one of the most hostile, violent, and honestly just fascinating environments on planet Earth. I'm talking about the inside of a modern Formula One power unit. We're going to explore the absolutely extreme thermodynamics at play here and really get into that razor-thin margin, that tiny line between winning a Grand Prix and suffering a total catastrophic engine failure. It's this crazy world where millions of dollars and thousands of hours of engineering can literally just go up in smoke in a fraction of a second. Okay, let's dive into this because the number 2,600 degrees Celsius really sets the stage for everything we're about to discuss today. That right there is the instantaneous gas temperature at the exact point of combustion inside a modern F1 cylinder chamber. Just to put that into perspective for a second, that is literally half as hot as the surface of the actual sun. And it's all contained within this block of metal sitting just inches behind the driver's head. The sheer extremity of this heat is just staggering. The internal packaging of these cars is so tight and these engines run so incredibly hot that mechanics have actually found burn marks scorching the car's carbon fiber aerodynamic bodywork. It's basically a fundamental battle against physics.
So let's move into Section 1, monitoring the heartbeat.
Right. So how do you manage a system that desperately wants to melt itself into a puddle of really expensive slag? Well, you need a trackside mission control. You've got about 15 to 20 highly specialized trackside engineers out there, split up between the pit wall overseeing the broad strategy and garage engineers focusing intently on just a single car. And they are constantly, and I mean constantly, monitoring hundreds of telemetry data channels every single second just to read the engine's heartbeat. The big takeaway here is that an engine failure in F1 often isn't just a sudden, unpredictable bang. Usually, it starts out as just a subtle oscillation in the sensor that tells the engineer on the pit wall, hey, if you don't tell the driver to slow down right now, that piston is going to exit the engine block in exactly 2 laps. Moving right along to Section 2, the hybrid heat problem. Let's zoom in from the pit wall directly into the actual physical engine architecture, specifically focusing on the hybrid systems, because since F1 went hybrid, the complexity has just absolutely skyrocketed. Modern F1 cars don't just use internal combustion anymore. They rely heavily on the MGU-H and the MGU-K. These are incredibly complex energy recovery systems that boost power immensely, but man, they add a massive, highly sensitive layer of thermal complexity. In fact, a lot of engine failures today aren't even the internal combustion part at all. It's the electrical integration. These high-speed electric motors generate massive amounts of heat. If the cooling system gets even a tiny little air bubble in it, the electric motor can effectively melt its own copper windings. Now, what's really interesting here is the sheer rotational speed we're dealing with. The MGU-H shaft, which is hooked up to the turbocharger, spins at a mind-bending 125,000 revolutions per minute. At those kinds of crazy speeds, the physical balance of that shaft has to be absolutely flawless. And let's look at how this builds into a catastrophic failure. Take the 2017 Honda RA617H engine during testing as a perfect real-world example. The massive lateral cornering forces from the chassis created these completely unexpected drivetrain vibrations. Those vibrations traveled right through the engine, causing that 125,000 RPM MGU-H shaft to lose its perfect microscopic balance. The shaft violently shattered, which then terminally damaged the internal combustion engine. From a broader engineering perspective, it's really helpful to compare an F1 engine failure to a total system breakdown on a major construction project. Just like one missing load-bearing beam can bring down an entire skyscraper, a microscopic vibration or a tiny blockage can literally bring down a $20 million racing project. Then you have the hybrid battery packs, which face their own terrifying threat: thermal runaway. If a battery takes an impact in a crash, or honestly just exceeds 100 degrees Celsius, it triggers an unstoppable chemical chain reaction. Within milliseconds, the battery hits 400 degrees Celsius, releasing all its energy in an event technically known as venting with flame. Yeah, it's a fire that conventional extinguishers can barely even touch. So all of this leads us to a pretty massive engineering question, doesn't it? How on earth do you stop a system that is this hot, vibrating this violently, and spinning this incredibly fast from just tearing itself to shreds? Let's find out in Section 3, the microscopic oil cushion. Surprisingly, the answer doesn't lie in some kind of solid metal, but in a liquid film thinner than a single human hair. This really brings us to the core margin of failure analogy. You have to understand that an F1 engine is designed to last only about 4,000 to 5,000 kilometers. That is wildly different from your standard road car engine, which is built to last maybe 300,000 kilometers. In F1, everything is vastly over-engineered for peak performance and purposely under-engineered for longevity just to save weight. Because the crankshaft spins so incredibly fast, the oil actually has to be heavily pressurized to create a physical cushion of fluid. And that brings us to boundary lubrication. This is the terrifying state where that highly pressurized oil film becomes just a little too thin under extreme load, risking direct metal-on-metal contact. And a Timken bearing test brilliantly illustrates what a successful oil film looks like under intense pressure. When applying severe pressure to a metal race-coated invalvoline oil, the oil pressure held up perfectly, maintaining that absolutely crucial fluid cushion. The metals never actually touched, leaving only a minor 3mm scar. In this scenario, the engine survives. But if that fluid cushion fails, well, this becomes your reality. In this particular test, the oil film succumbed to the pressure and just broke. The result? Instantaneous metal-on-metal screeching, leaving a catastrophic 8mm gouge. Inside a running F1 engine, this level of friction is an absolute death sentence. So the crucial point we really need to understand is piston scuffing. If the oil pressure drops for even a fraction of a single second, the metal piston physically touches the metal cylinder wall. The immense friction generates so much instant heat that the microscopic high points of those two metals actually localized weld themselves together. At 15,000 RPM, that friction heat effectively welds a multi-million-dollar engine together from the inside out, destroying the whole thing instantly. Which brings us to our final part, Section 4, the margin of failure. When you zoom back out and look at the big picture, you really start to realize just how precarious this all is. The entire multi-million-dollar operation rests on a knife's edge. This quote from Honda during their super turbulent 2017 season perfectly captures that harsh reality. An engine failure isn't just bad luck. It's often related to what engineers call thermal expansion coefficients. Basically, different materials like steel, aluminum, and exotic ceramics expand at completely different rates when they get hot. This is exactly why warming up an F1 engine perfectly is so absolutely critical. If you push the engine before the metals have expanded to their exact operating tolerances, your oil film drops, your shaft vibrates, and suddenly you've got a persistent, catastrophic failure on your hands. And that brings us to the end of our explainer today. We've seen just how incredibly tight the margin of failure really is when you're balancing extreme heat, microscopic oil films, and massive hybrid complexity. So I want to leave you with a question for our next deep dive. What part of this equation fascinates you more? Should we explore the materials science next, like why they use Inconel and exotic alloys to survive these crazy temps? Or should we look at the systems integration, how the hybrid software actually controls the engine on a millisecond by millisecond basis? Think about it and let that fuel your curiosity until next time.